Okay, now for the second half of this lesson. Let's see, the first thing we need to do is find the derivative. Here we're on example 5. Use the first derivative test to find the local extrema of this. So our derivative would be 6x squared minus 6x minus 72. Then you set that equal to 0, so you can find the critical values here. And hopefully we can factor and solve. I believe we can on this one. We can factor out our GCF. That makes it a lot easier to solve. And that factors, thank goodness, to x minus 4, x plus 3. So using our zero product property, we know x is 4 and x is negative 3. So these are our two critical values. Wow, that color is not showing up very well. So I'm going to turn this light off and see if that makes a difference. Wow. A little bit. Okay, so we're going to try it like that. It's interesting, but we'll see. At least you can see the ink a little bit more. So that's our critical values. So we have negative 3 over here, 4 over here. And we're going to test a value over here, let's say negative 4. Let's test 0 in the middle because that's a nice easy number to work with. And then test a number on the other side, which is 5. Now you can pick different values to test, and that's absolutely fine. Just pick something you want to work with. So if I plug in negative 4 into the derivative, that gives me 48. If I plug in 0, I get negative 72. And if I plug in 5, I get 48. Again, it's coincidence those two numbers are the same. Not always going to be that way. So notice this one's a positive, this is a negative, this is a positive. So this means there's a positive slope here, and then at that point it switches over to a negative slope. This one starts off as a negative slope and then switches to a positive slope. So this means there's going to be a local max right there and a local min right there. So you're going to write local max at x equal negative 3 and a local min at x equal to 4. Now for example 6, we're going to do the same thing, only it's a little bit more complicated because of the rational expressions there, or the rational exponents. So we're going to find the derivative. So the derivative of this would be, this would be 4x to the 1/3 minus 4x to the negative 2/3. And if you need to show that step where you're multiplying 3 times 4/3, you can, but the 3 is canceled out, which is why I just went ahead to the simplified one. And I'm going to clean it up a little bit. This would be 4x to the 1/3 minus 4 over x to the 2/3. Now, to work with this, the easiest thing to do is to get this together as one term and get a common denominator here. So remember, this is like over 1, and our common denominator is going to be x to the 2/3. So that means this one, this first one, I'm multiplying by x to the 2/3 on top and bottom. So that gives me 1x here at the top. Well, I should say 4x because x to the first power. And then the second fraction I'm not changing, so that stays the same, over x to the 2/3. Now to find my critical values, remember that's everywhere that the derivative is 0 or it is doesn't exist. So we can take our numerator, set it equal to 0 and solve, and our denominator, set it equal to 0 and solve. So here I get x equal to 1. Here x would be 0. So those are our critical numbers. So we're going to test it. I'm going to put it over here. We got 0, we got 1. That means I'm having to check a fraction. I'm going to say 1/2, which if you want to write it as 0.5, because I know you like to put that in your calculator, you see here 0.5, that's absolutely fine. Here I'm going to do 2. Here I'm going to do -1. I'm just trying to find the easiest numbers to work with. So if I plug in -1, let's see what that gives me. I don't even have that one worked out just yet. But on the top, that would give me 4 times, I don't even know why I'm writing this out, because that's easy enough to do without a calculator, but I have a feeling y'all are doing it too. So the top is -8. The bottom's also going to be negative. Oh goodness, hold on, let me see what's going on. Okay, I'm back. That was just somebody walking down the street. Anyway, the top would be -8, the bottom would be a +1, so this gives me a -8. If I plug in 0.5, that gives me about -6.35. And if I plug in 2, I get 2.5. So notice that I have a negative, then I have a negative, and then I have a positive. So what this means is there's no local extrema at 0. But there is at 1. So if I'm going from a negative to a positive, this is a local max. I'm sorry, local min at x equal to 1. Now in example 7, we're going to use that first derivative test again. This one's a little bit more complicated just because you've got that quotient there, but you should know how to do that. Shouldn't be a big deal. We're going to remember our quotient rule, low d high minus high d low over low squared. So low d high minus high d low over low squared. Then we kind of clean that up. And so our derivative would be negative x squared plus 1 over x squared plus 1 squared. So when we're looking at this one for our critical numbers, we can actually just take our numerator and put it here because we're never ever going to have 0 on the bottom. So I get 1 equal to x squared, so x is a positive or -1. So that means our critical numbers are going to be -1 and 1. So we have to test on either side of that. So we're going to test where x is -2, x is 0, and x is 2. So if I plug in -2, that gives me -3 over 25. If I plug in 0, that gives me 1. If I plug in 2, I get -3 over 25. So notice it's a negative to a positive to a negative. So negative slope to a positive slope to a negative slope. So that means I have a local min there, a local max there. So let's write it over here. Local min at x equal -1 and local max at x equals 1. And you can look at the graph and of course get that same information. Okay, now sir, example 8. Find all local extrema of this particular one. Now the reason I like this one is because it has the e's in there. A lot of times you guys forget how to find derivatives with the e's, so we're going to go over that. Notice we do have to use the product rule on this one because we have the x squared times e to the 5x power. So our derivative would be the first one times the derivative of the second, which would be 5 e to the 5x. Then we have plus the second one times the derivative of the first one. Then at this point, I'm going to factor out from like this chunk and this chunk. I see they both have an e to the 5x power. So just to kind of clean it up, I'm going to put that in the front. And I'm going to leave the other stuff there. I know they do have an x in common, but I'm going to leave it there and deal with that in just a moment. So at this point, remember if I'm looking for my critical values, I'm setting this equal to 0 and solve. So I know that either e to the 5x has got to equal 0, or 5x squared plus 2x is equal to 0. Now this doesn't work. Like if you try to solve that, get an answer, you're getting an error message. That's a domain issue. So you're really not having to worry about that. But this side, we could factor out an x. So I know x is 0 or x is a negative 2/5. So those are our critical values that we're looking for. So 0, no, negative 2/5 would be first, then 0. Okay, so that means I'm going to check, say, -1, negative 1/5, and 1 as my test values. So when we plug this in, the derivative of -1 would be, that's about 0.0202. I'm just rounding this stuff off. If you plug in negative 1/5, and you guys can take the time to plug it in yourself and see what you get, should get the same thing. If not, let me know so I can see what the problem is. We can figure it out. If I plug in 1, I get about 19.028. So notice I'm going from a positive to a negative to a positive. So that means we have a local min at x equal negative 2/5 and a local max at x equal to 0. Now for the last example, this one is challenging. We may need a little extra room to work on it because when we're going to find our derivative here and then we go to find our critical values, it doesn't automatically, or I shouldn't say automatically, it doesn't factor. So it's not as pretty as some of them. So we're going to have to use our quadratic formula to solve this one. So I wanted you to see it because sometimes the numbers at this level just aren't that pretty, but you need to be able to do it anyway. Okay, so on example 9, the cost function in millions of dollars for Priceline Group Inc. can be approximated by this function, where x equals 0 corresponds to the year 2000. Determine when costs are increasing and when costs are decreasing. Also find all local extrema of the cost function. So I left the picture. The picture looks beautiful. We could not draw it to be any prettier than what it is right there. However, we can see that there's a section that is decreasing, there's a section that is increasing, so that's going to help us confirm our numbers, but we don't know exactly what those points are because it's not exactly on a specified line. Okay, so we are going to solve it the normal way and just use that to confirm our answer. So the first thing we want to do is find our derivative. So when we take the derivative of this, that would give us negative 7x squared plus 106x minus 295. And then we have to set that equal to 0 and solve. So to find our critical value, so that's what I'm going to do here. I factored out the -1 first, thinking that this would factor, and that's what I attempted, that's what I tried, but it turns out that wouldn't factor. Of course not, right? That would be too easy. So now let's use our quadratic formula. So x would be equal to negative b plus or minus the square root of b squared minus 4 times a times c, and the whole thing is over 2a. So you should remember your quadratic formula. If not, write it down. But that's essentially what I did. So if you put all of that under your calculator, or in your calculator, you get 106 plus or minus the square root of 2976 over 14. So x is about 11.5 or x is about 3.7. Okay, so those are the two values. You could double check that for me by plugging it in your calculator, but that's what I got. So these means these are our critical numbers. So when we draw our little test intervals here, remember we're picking one in each part. Over here I'm going to put 0 because it's a nice easy number. Here I'm going to do 10. Here I'm going to do 15. So if I plug in 0, easy enough, I get negative 295. If I plug in 10, I get 65. And if I plug in 15, I get a negative 280. Now I'd like you to pause the video and just do the math yourself and make sure you're getting the right numbers with your calculator. You know, take the time to do that. But the negative, positive, negative thing, that tells us that The local min is at x equal to 3.7, and local max is at x equal to 11.5. Now you can always adjust this to say what it actually means. This would be 2003 and 0.7, as far as it's going to be in the year 2003. And the other ones be, probably halfway through 2011 for the local max.